discussing a presentation by Angela Dai from Technische Universitaet Muenichen. It's about modeling 3D images from RGB data. Now, the presentation itself is fairly weak, but I still want to discuss it because it's an area that we're very interested in, and that is, can we take camera images, RGB images, so three-dimensional images, and can we model objects from those images? And this is along the lines of some work that we've discussed recently from Stanford, where basically, can we see physics, right? Can we, just by seeing something, infer the physics of an object? Now, this work is going into that direction. I think Angela is probably a very, very good researcher. Her papers and presentation are very cumbersome, so it's painful to go through it, but still there's obviously a lot of interesting science there, so we still want to discuss it. So the idea is that you use actually CAD models to calibrate a picture. So there's a three-step process here. One is you take in the image, then you use diffusion to improve the image, and then you use that as a prompt for a CAD model. So you have a transformer-based architecture here with diffusion and with a probabilistic assignment of what the prompt looks like. So if I see a chair, I then align it with a CAD model of a chair that is most similar to the chair that the diffusion model has produced. So again, in a very simple way, what Angela and et al. Are doing is try to see and then infer geometry and hopefully physics of the object. And she's doing that in virtual space in the hope to generate synthetic data for robot learning. This is not even on podcast. It's September 1st, 2024. This is Crindelco. It's Sunday. There's no update. For the year, we are up 6.6%. The market's up 18.4%. We're underperforming by 11.8%. So Angela Dai, in her presentation at the GRASP seminar, is talking about her work in taking 3D images from RGB data and translating them into virtual objects that are similar, basically recognizing the objects from camera and then representing them in virtual space as realistically as possible. This is the first step. The second step, then, she is talking about human-object interaction in one of her papers. The links are in the show notes. So the next step would be then to take an object that you see in the camera and that you understand how this object can be interacted with. For that, she's creating a synthetic data set of human object interaction instances. So you have a cup, and what she's modeling is how this cup moves if you hold it and push it back and forth or up and down. And the way she's doing that is, again, she's using sort of a plethora of contemporary models, so diffusion and transformer architectures, to model not just the geometry of the object and the geometry of the body part that is approaching the object, but also the distance. And then as you get closer to the object, she's incorporating the physics of the body part that is going to interact with the object, so she can then model how the object will move in conjunction with the body part. In other words, how will a cup move if you hold it? So the way she looks at this is, you can look at this, it's not a robot manipulating the cup, but it's the cup being manipulated by forces that are inherent in the body part, let's say in the arm, and those forces through the arm are being injected in the cup. So for example, you could look at it that way. Now, why is this all important? Of course, for us here at Orange Capital Partners, we're laser focused on the humanoid robot side of things. We're trying to understand what the humanoid robot space looks like, what are the scientific obstacles and also what are the opportunities. And I think this is the kind of work that I hope will get us to potential resolution of some of the hardest problems in robotics, the Moravec paradox, which is the very simple stuff for humans, lifting a cup, putting an iPhone in a drawer, all that stuff is really difficult for a robot. And I think this kind of work is going in the right direction in trying to solve some of these problems by first by even understanding what is it I see. And the way Angela et al. Model this is they use CAP models because, look, when we see a cup or when we see a chair, what we really see is potentially kind of a form of a CAP model, right? We see a geometry. Obviously, we don't explicitly think like that, but we might still, somewhere in latent space, somewhere in our brain, there's a model that tells us that I can sit on that chair. And if the chair only has 3 legs, my model is telling me I can't sit on that chair, at least not safely. And if that chair doesn't have a stable back, I can't just lean back. Like these things are all inherent, but I think what Angela et al. Are doing is they're using a CAP model to explicitly create a reproduction of a chair that is actually being seen in real life. So the camera sees a chair, and then whatever is seen is being aligned with the CAP model. So we have a mesh network of geometry that matches this chair, and then we can work with this, right? Once we have this representation in virtual space, we can then work with it. For example, we can use it for video games, or we can use it to generate synthetic data for, let's say, robot learning and things along those lines. So I want to just mention this presentation because I think everything that has to do with vision and physical representation of reality is, in our opinion, absolutely crucial for the advancements of robotics. Because how else can we, have a humanoid robot walk around the factory, pick up tools, and potentially even use those tools, right? We need to understand first, what is it we see? What are the geometries of the things we see? What are the physics of the things we see? Now, we might be able to infer that implicitly, so we don't have to explicitly program it, but we need to understand what we see, right? And the tool has a certain geometry, and then maybe we can learn, or maybe we can explicitly have physics constraints in there. So, for example, the tool is heavy, the tool is not heavy, things like that, or we can just learn it from vision. So this, of course, requires even more data. But I guess my point in principle here is to come back to Jensen's comments on the earnings call, right? We have data and we have search. And I think this is the new problem statement of AI that we abide to. And I think we want to kind of think along those lines. We want to think along those lines. So everything in AI, in our opinion, is going to be driven around data and search. So in this cases, first we take in the vision. So we take in the virtual picture, the picture of a chair or a car or a tree. We then use stable diffusion or some sort of diffusion to better represent the tree. Then we use as a prompt to align it with a CAP model, and now we have a precise geometry of the tree, the closest possible tree or chair or car that we could find in our CAP model database that is generated from data that is trained on CAP models. So we have basically an alignment of that thing we see. And then once we have that, we then use that geometric representation of the thing to model human-object interaction. Now, where this is going is, of course, and the crucial question is now, once we have a representation of the geometry, where do we stand with the physics? I think that's a very interesting problem in itself. And I believe that that is probably going to be, and I'm sort of paraphrasing Sergey Levin here, I think we need to bootstrap ourselves here. we can't explicitly program the physics into our models. So what we can do is have, thousands and millions of interactions with a certain chair, with a certain car, with a certain object that we have now represented as well as we can in geometry space, and then learn through these interactions what the actual physics are like. This is a little bit looking forward. This wasn't discussed in this particular presentation, but this is us just looking forward. So again, I think to summarize, Angela Dai's work is really interesting for the ability to see an object and represent it as accurately as possible in geometry space by aligning it with a CAD model, computer-aided design, and then model the interaction with the object. And from there, we are going towards the physics. Now, she's not explicitly going there yet. All she's trying to do is just model the interaction itself. So have the cup move in conjunction with the arm that is holding, or the hand that is holding the particular cup. So that's the goal here. But of course, the next step would be then to have a further modeling of that cup, how it acts when it's being held, when it's being lifted. Next thing you could think of is also, for example, what happens to the cup if it has water in there or coffee, if it gets heavier or lighter. So those are all questions that kind of bring us into a subsequent scenario. But I think for now, again, I think just to summarize again the paper and the presentation of Angela Dai, what we want to do is see something, have it represented as accurately as possible, match it with a CAD model to have the geometry, and then use that to model the interaction of the object with let's say a human limb, like let's say a hand or a ball that is being kicked by a foot. Thank you.